Hello, this is a video on electric field calculations. I'm following Young and Freedman's University Physics, and he gives a number of examples in this section. When I introduced electric field calculations in the previous video, we talked about, let's say you've got a point out here, and you've got a dipole, which is two oppositely charged point charges of equal magnitude. What would be the electric field at this point out here? And so now we want to do a second example from this section, which has to do with I fell into a ring of burning charge, which doesn't exist. Never mind. Johnny Cash. I don't like country music either. So let's move on. Okay, so let's say we've got a ring-shaped conductor with an evenly distributed charge. So it has a radius A, and it has a total charge Q. So the infinitesimal charge is dQ. Not Dairy Queen, but D charge. And so this is an infinitesimal dQ. So what would be the electric field at point P, out in the middle of nowhere, out from the axis, the x-axis of this ring of charge at distance x? That's our question for today. This is example 2110. Okay, so first of all, the y component is going to cancel out, because the field lines from the top will be going in the opposite direction as the field lines from the bottom. So for example, if the field lines are coming out from each point toward the center, then these field lines are going to be coming this way, and these fields are going to be coming this way. Let's say it's pulling it in, negatively, then it's going to be going this way, it's going to be going this way. Either way, the y component is going to cancel out, which makes things really nice because we can just ignore it. All right. Now, let's imagine, as I've said, that the charge distributed throughout this ring is distributed in infinitesimal little units of distance, ds, with infinitesimal charges, dq, not Dairy Queen, creating infinitesimal little fields, de, okay? It's a little calculus there. So what's going to happen? Well, we know this remember this field equation? We've had this now for several sections and several videos. So this is the basic equation. 1 over 4 pi epsilon naught is 9 times 10 to the 9th power Newton meters square per Coulomb squared, or something like that. It's a constant. It's a constant. And so we've got that. So that means that dE, the infinitesimal field, is going to be 1 over 4 pi epsilon 0. dQ, not Dairy Queen. Stop saying that. Over x squared plus a squared. Why x squared plus a squared? Because what is r squared? Let's go back. What is r squared here? R squared is this squared. And a squared plus b squared equals c squared, right? So a squared plus x squared, the square root of that is going to be r, right? Okay, it's Pythagorean theorem. Again, man, that's paying off. Glad I learned that back in middle school. Okay, so this is what this turns out to be. R squared is x squared plus a squared equals r squared, right? A squared plus b squared equals c squared. Okay, so there we have it. We have the infinitesimal equation. Now, so dex, that is the x component coming out from that ring, from each the infinitesimal x electric field component is going to be dE times the cosine of alpha. What is the cosine of alpha? What is alpha? Well, alpha is this little fish right here. And so the cosine is the adjacent x over the hypotenuse, square root of a squared plus x squared, right? That's what a cosine is. So when we come back here, the cosine is x over the square root of x squared plus a squared, which I just showed you, okay? So now we can find out what the infinitesimal field x component is. It's going to be all of this, dE, there it is, times the cosine of alpha, all of this. And there we have, it looks awful, but it's not that hard. If you think of it in pieces, we've just put it all together. Okay, so when I take this, I'm going to simplify it. When we get to the next page, I'm going to put the x in front of here. And this is 1 plus a half is 3 halves, right? Bam! It shouldn't be 3/4. Man, what is wrong with me? Hold on a second. Phew, I feel better. Don't you feel better? It's 3 half. Oh, it's wrong up there. What's wrong with me? Okay, there it's right. I breathed into a paper bag for several seconds. I feel much better. A little lightheaded though. And he's back. Okay, so now what I want to do is I want to get it out of the infinitesimal form into an EX form. So I'm going to integrate. Of course, you knew there had to be some calculus in this video somewhere, right? I'm going to take the integral of all this. That's going to take the infinitesimal out. I'm going to add up all those little infinitesimals. I'm going to add them all up, and I'm going to get the integral of all this stuff. And so what's it going to be? Well, 1 over 4 pi epsilon naught, that's a constant. X squared is a constant. A squared is a constant. This is a constant. In fact, X, okay, well, X, what is X? Is X a constant? X is a constant. Yes, X is a constant. It's the distance out from the ring, right? It doesn't change. So the only variable is dq. And so we're going to get rid of Dairy Queen, and it's going to become q. And so there we have it. We took all the constant stuff out, and then we integrated dq, which becomes q. It's very simple. And so we know that EX equals all this. And then if we put the vector, if we put the vector I there, then that tells us it's going in the X direction. And I think we're done. Yeah, we've done it. This is the example. And because Young and Freedman have not done this with actual numbers, this is the formula. This is the formula for finding the electric field at a certain distance on the axis from a ring of equally distributed charge. Bam, there you have it. And since you all have photographic memories, just memorize that for the next time you have this sort of a problem. Well, okay, there we have done yet another of his examples. There are 2 more to come.